In this video, we're going to talk about how to represent a function as a geometric power series by differentiation. So our first example is going to be f of x is equal to 1 divided by 1 minus x squared. So what do you think we need to do in order to represent this function as a power series? We need to put it in this form, a over 1 minus r. So that's the sum of an infinite geometric series. So basically, we need to make it look something like this, 1 over 1 minus x. It turns out that if you integrate this expression, you're going to get 1 over 1 minus x. Likewise, if you differentiate this expression, you're going to get what we see here. And let's show that. So let's take the derivative of 1 divided by 1 minus x. So the first thing we need to do is rewrite the expression. So this is 1 minus x raised to negative 1 power. And using the power rule, it's going to be negative 1 times 1 minus x to the negative 2. And the derivative of 1 minus x is negative 1. Negative 1 times negative 1, that's going to be positive 1. And then taking this term, bringing it back to the bottom, that's going to be 1 minus x squared. So the derivative of this expression gives us the function that we want to represent as a power series. Keep that in mind. Now let's represent this function, 1 over 1 minus x, as a power series. So it's already in the appropriate form. So let's set it equal to a over 1 minus r. So we can see that a is 1 and r is x. So using the geometric series expression from 0 to infinity of a times r to the n, we have 1 times x to the n. So therefore, we could say that 1 over 1 minus x can be represented by the power series starting from n equals 0 to infinity of x to the n. Now, if that's the case, we need to take the derivative of both sides. So the derivative of 1 over 1 minus x, we know it's 1 over 1 minus x squared. So all we need to do is differentiate x to the n. So we're going to have the power series from 0 to infinity, and the derivative of x to the n using the power rule is going to be n x to the n minus 1. Now let's write out the first 5 or 6 terms. So this expression is equal to, when n is 0, this is going to be 0 times x raised to the negative 1. So all of that is just going to be 0. Now when n is 1, we're going to have 1x to the 1 minus 1, or 1x to the 0, which is just 1. And then when n is 2, it's going to be 2x to the 2n minus 1, or basically 2x to the first power. And then when n is 3, it's going to be 3x squared. And then the next one is 4x cubed. And then you can see the pattern. After that, it's 5x to the 4th and so forth. Now, notice that the first term is 0. Adding 0 to something doesn't change the value of anything. So therefore, we really don't need to start at 0 because it's just not necessary. So we can write our final answer like this. So we're going to start at 1 and go to infinity, and it's going to be n x to the n minus 1. So this is the final answer. Sometimes you may need to find the interval of convergence for your answer. So what is the interval of convergence for this particular power series? Now keep in mind, that power series was produced as a result from a geometric power series. And earlier in this problem, we said that we use this particular geometric power series. And for any geometric series, it converges when the absolute value of r is less than 1. So notice that r is x for this particular geometric power series. So we could say that the absolute value of x is less than 1, which means x is between 1 and -1. And this right here tells us the radius of convergence when it's in the form absolute value of x minus c is less than r. So the radius of convergence is 1. Now this is the interval of convergence for the original geometric power series. For the new power series, which was obtained by differentiation, the interval will be very similar. However, the endpoints, it may change. So we need to check for the endpoints. So let's start with -1. If we replace x with -1, we're going to get n raised to the -1 times n minus 1. And using the divergence test, we can see that this is going to diverge. We have an alternate series, and so our a sub n is n. So the limit as n goes to infinity for a sub n, that's going to be infinity. So the series diverges, which means that it will not converge when x is -1. So -1 is not included. So far we have this. So we're going to have a parentheses at -1. Now we need to see if we're going to have a bracket or parentheses at +1. So let's plug in +1. So this is going to be n raised to the times 1 raised to the n minus 1. 1 raised to the n minus 1 is still 1. So this becomes just n. And based on the divergence test, this too will diverge. In this case, the interval of convergence for the new power series after differentiation is still the same as the original geometric power series. Let's consider one more example. Consider the function f of x, which equals 1 divided by 1 plus x raised to the third power. So go ahead and find a power series representation for that function. Somehow, we'll need to convert that function into this form, 1 over 1 plus x, because that's similar to the sum of an infinite geometric series, a divided by 1 minus r. So what do we need to do to convert this expression to this? If we integrate this expression twice, it's going to give us something that looks like this. And if we find the second derivative of 1 over 1 plus x, then we should get this expression. So let's verify that. Let's find the second derivative of 1 divided by 1 plus x. First, we need to rewrite the expression. So we need to move this to the numerator. And so this becomes 1 plus x raised to the -1 power. Using the power rule, it's going to be -1 times 1 plus x, and -1 minus 1, that's -2, times the derivative of the inside part, 1 plus x, which is 1. Now, we need to differentiate it one more time. So this is the first derivative, and we need to find the second derivative. So we need to bring down the exponent, -2, and then it's going to be 1 plus x. -2 minus 1 is -3. And so we can rewrite that as 2 over 1 plus x raised to the third power. Now let's write down what we know. The second derivative of 1 over 1 plus x, we've determined that it's equal to 2 over 1 plus x to the third power. which is 1/2 of the function that we're trying to represent as a power series. So let's begin by writing the power series for that expression. Now what we need to do is change the positive sign into a negative sign. So a positive sign is equivalent to two negative signs. So 1 plus x is the same as 1 minus negative x. And now it's in the appropriate form. So we can see that a is 1 and r is negative x. So using the series a times r to the n, it becomes 1 times negative x to the n. And negative x is basically negative 1 times x. So we need to distribute the n to negative 1 and x. So therefore we could say that 1 over 1 plus x, that's equal to the series starting from 0 going to infinity of negative 1 to the n times x to the n. Now let's go ahead and take the derivative of both sides. That is the second derivative of both sides. So we know the second derivative of 1 over 1 plus x is equal to this. So that's 2 over 1 plus x to the third power. So that's on the left side. On the right side, we need to find the derivative of this expression twice. So what is the derivative of negative 1 to the n times x to the n? Well, we need to recognize that n is a constant, x is the variable. So first we need to rewrite the constant and then take the derivative of x to the n, which is n times x raised to the n minus 1. So this is the first derivative. Now we need to do it again to get the second derivative. So this time, negative 1 to the n times n, that whole part is a constant. So we really need to take the derivative of x raised to the n minus 1. So using the power rule again, we're going to bring down the n minus 1 exponent to the front. So it's going to be times n minus 1 and then x. And then we need to subtract n minus 1 by 1, which becomes n minus 2. So thus we have this expression. So from 0 to infinity, negative 1 to the n times n minus 1 times x raised to the n minus 2. So that's the power series for this function. Now we need to get rid of the 2. So what we're going to do is multiply both sides by a half. So half of 2 is 1. So we could say that f of x, which is 1 over 1 plus x to the third power, that's 1/2 of the series from 0 to infinity of negative 1 to the n times n minus 1 times x raised to the n minus 2. Now, it turns out that there's more than one way to represent the power series that corresponds to this function. So to find out another way to represent it, let's write out the terms in the series. So when n is 0, what value do we get? 0 times 0 minus 1 times whatever, that's going to be 0. Now the second term, when n is 1, 1 minus 1 is still 0. Now when n is 2, this is going to be 2 times 2 minus 1, which is still 2. And then x to the 2 minus 2, that's x to 0, which is 1. So this whole thing is 2. And then negative 1 squared, that's 1, times a half. So this is going to be plus 1. Now the next term is going to be negative. So when n is 3, this is going to be 3 times 3 minus 1. So that's 3 times 2, which is 6. Half of 6 is 3. So this is minus 3x, and then 3 minus 2 is 1. And then the next term is going to be positive. So n is 4. 4 times 3, that's 12. Half of 12 is 6. And then this is going to be 4 minus 2, so 6x squared. And then you can continue the pattern. So notice that the first two terms we do not need. So if we want to, we can replace n equals 0 with n equals 2 if we want to. Because if we start counting at 2, we're going to get this expression, which still has the same value as the original series. If we add 0 to 1 minus 3x plus 6x squared, it's going to be the same. So you can write this as n equal 2 or as n equals 0. Now I have a question for you. So we saw that if we make n equals 2, we're going to get the series without the 0. And if we make n equals 0, we're going to get the entire series with the two zeros. Is there a way where we can change this to n equals 0 and at the same time neglect these two zeros, only get everything starting from 1? So how can we get this particular series when n is equal to 0? So think about that. See if there's a way in which we can do that. And it turns out that there is. So let's make this n equals 0. So to make this work, what we need to do is basically add 2 to every n value that we see. So first, let's add 2 to this value. Negative 1 to the n, is that the same as negative 1 to the n plus 2? Negative 1 to the n plus 2 is negative 1 to the n times negative 1 squared. And negative 1 squared is positive 1. So therefore, these two expressions are the same. So if we add 2 to it, we really don't need to change it. We can just leave that as negative 1 to the n. For everything else, we need to add 2 to every expression that contains an n in it. So the function 1 over 1 plus x cubed can now be represented this way. 1/2 of the power series from 0 to infinity. And negative 1 to the n, we don't need to change that. Now this part n, we're going to add 2 to it, so it's going to become n plus 2. And then if we add 2 to n minus 1, negative 1 plus 2 is positive 1, so it becomes n plus 1. N minus 2 plus 2 becomes just n. Now, if we plug in 0, 0 plus 2 is 2, 0 plus 1 is 1. So this is 2 times a half, and then x to the 0 power is just 1. 2 times a half is 1, so that's going to give us the first term starting from this point. That is starting from 1. Now when n is 1, I'm going to write this one out. So it's going to be negative 1 to the first power. 1 plus 2 is 3. 1 plus 1 is 2. And then x to the first power times 1/2. So this is going to be, these will cancel. So we're going to get negative 3x. And then let's try one more just to make sure. So when n is 3, this is going to be negative 1. Actually, when n is 2. Here, this is for n is 0, 1, and 2. So when n is 2, we should get 6x squared. So this is going to be negative 1 to the second power, and 2 plus 2 is 4, 2 plus 1 is 3, times x to the n is 2, so x squared, and then times 1/2. So negative 1 squared is 1, 4 times 3 is 12, and half of 12 is 6. So we're going to get positive 6x squared. So it gives us the exact series, the same series, just without the two zeros. And so this is our answer. So that's the power series representation for the function 1 over 1 plus x to the third power.